Welcome to lesson 1.3, and this begins in your book on page 24. This is a lesson on functions, whether they're continuous or discontinuous, their end behavior. Some of it's review, some of the terminology may be a little new. First of all, let's talk about what makes a function continuous, which means you can basically put your pencil on one end and you can just draw it and there are no gaps. Let's write that down. No gaps. No holes. Remember, there are no holes in the graph. It doesn't stop existing at one point and then jump onto another part. Basically, there are no breaks. Okay, so any of that terminology that helps you remember. Now, you can have several different types of discontinuous functions. If you have a function that approaches asymptotes, for example, and it's approaching negative infinity this way, or it's approaching positive infinity if you approach that asymptote, then this type of discontinuity is called infinite discontinuity. Infinite discontinuity. And basically, you have separate branches that go to infinity or negative infinity. Okay? This type of a graph, you're going along here, you're coming in, and you exist, but then you jump down here. You don't go any further past that axis, but you jump down here and you go further from that point. So what's happening is the function is existing at every point, but it's jumped right here. So it is discontinuous at that value. It's like up here, it exists other places, but it does not exist as you're approaching that asymptote. So it's discontinuous, the whole function is. Here it is not continuous all over. You would have to jump. So this one is actually called jump discontinuity. And it breaks in the function. It breaks, but it exists at all points. The function exists at all points. And this one, the function's just going along and boop, it doesn't exist there, and then it keeps on going. So it has been removed, the function existing has been removed at that value. So it has what's called removable discontinuity. Removable discontinuity. So the phrases are pretty self-explanatory. This one has a hole at a point, and so you can remember. This one is probably going to be your piecewise functions when you have those, especially if you are judging the discontinuity or the continuity at a specific point that it has the jump. Let's look at a couple examples. First of all, let's determine if the function is continuous. If not, how is it discontinuous? Well, this function here of x cubed, remember that's going to be a function that's going to, and it's positive x cubed, so it's doing this number, right? And if I want to know, is that continuous when x equals 0? Well, yes, right? The whole function is continuous, and it does exist when x equals 0. So it is continuous. Yes. Okay. Let's look at this piecewise function. And I want to take a moment to talk about how to graph this in the calculator, because some of you may not know how to do that. So when you're graphing this function, you're going to put in each of the different pieces, but you have to put them in parentheses. So if you notice, I've put 5x plus 4 in parentheses, and then I'm going to divide it by the restriction. So when you put that in the calculator, going to divide it by the restriction right there. And in order to do that, I have to use the greater than, less than signs, and you may not know where those are. They're right here at test. So you're going to go second test, and that will give you the different pieces that you want. Okay? And that will help you when you're graphing the restrictions. Let's go back there. So I've put both pieces in. Now I want to know if it's continuous or discontinuous at x equals 2. So when I look at my graph, I only see one line. Well, I know full well that this is two different lines. And this one, when x, let's say, is less than 2. So when x is 0, I would be at 2. So this line is what I see on my screen. This top line right here, when x is greater than or greater than 2, if I plug 2 in here, I've got 10 plus 4, I'm at 14. My graph just doesn't go that big. All right. So if I want to, I could zoom out and I could see this graph. I could also change the window if I wanted to. Zoom out. There it is. It's way up here. Okay. So it jumps. It came in to that value and then it jumped up there. So we have it is discontinuous at 2. It jumps. Now let's talk a little bit about the specific type of answer and how you want to phrase that. So I think let's say that it is discontinuous. All right, and I'm going to abbreviate that. So as you're approaching 2 from the left, okay, so from the left, you can see that the function is approaching what value? It's approaching the 0. It's a little bit hard to tell here because we've zoomed out, but it approaches from the left as x approaches 2. The limit of the function goes to 0. But as you approach it from the right, as x approaches 2, the function is at what value? Remember, if we plugged in 2, then you were at 14. Okay, so you have a jump discontinuity. T at x equals 2. All right. Now let's talk a little bit about something where you can approximate the zeros. All right, let me get that set up. All right, now I'd like to approximate the interval for zeros. Let me tell you just kind of big picture what we're doing. I'm giving you functions and you are telling me different characteristics about them. And ideally you want to get to the point where you can do this without the calculator and graphing it. But graphing it is one of your tools, and sometimes you can graph it on the calculator. Sometimes you're making a table. You're looking at the table on the calculator. Sometimes you're trying to figure out the behavior of this function, and therefore you can predict what's going to happen at a certain point, certain value. So some of the times we need to know where the function is going to have a 0, is going to cross the x-axis. So for example, let's look at this function. The function of the quantity x squared minus 6 divided by the quantity x plus 4. Now I'm only interested in this function between the interval of -3 and 4. And I want to know where the zeros are going to happen between those intervals, or that interval of -3 to 4. And it could happen in a couple places. We have to figure that out. So when you graph it, to get an idea, now you could make a table. You could plot the points between, start at -3, then do -2, then -1, 0, etc., and go up to 4 and see what the values are. I would like to, I'm a visual person, right? So I want you to see what the graph looks like. And when you graph it, I did change the window a little bit so you could see. You're going to have 2 branches, right? Because you have an asymptote here at -4. So at -4, but I'm not going all the way down to -4. I'm only starting at -3. And it looks like from -3 even to -2, it looks like I have a cross right there. I have a 0. And then over here, it looks like I have one between 2 and 3. Okay? Now, as I said, you can plug in the values. You can verify that. You can also go to the table. And if I start the table at -3, I plug in that value, I get these values. And you can tell this is pretty obvious because it crosses from a positive to a negative. So you know that there is a 0 that exists in between the -3 and the -2. And also, you can determine by looking at all these that there is one right here because it's negative and then goes positive. So you know there's another one between 2 and 3. So I'm just going to write that the interval would be between -3 and -2, and then also between 2 and 3. Those would be where the intervals for the two zeros for that particular function. Now I'd like to try another function. This particular function graphs from this equation right here from -5 to 0. Okay? And this graph, when you look at it on the calculator, looks a little different. Okay, it does one of these little snake turns. All right, and we're going to talk about what you see with this graph and what happens when we come back in the next video. All right, so this is the end of part 1. I'll be right back.